My name is Selçuk Borovalı, but it appears that my son's, I think I'm using my son's account, so sorry about it. Now I'll try to share the screen and start the presentation. Okay. I think you can see the presentation. Well, I am going to talk about biodiesel, bioethanol, and biojet fuel, and try to summarize the production processes very briefly. I'm not going to go into details, but you're more than welcome to ask any questions if you wish, and try to answer or talk about the current advancements. And I want to share a few words about the possible future, some reference data, and my thoughts about the future of biofuels. So, you know, the biofuels starts from the biomass originally, and it is in the form of liquid, in the form of a mixture. It can be in the form of solid waste, agricultural residue, food residue. It can be used cooking oils, anything we call biomass. Well, there are a couple of alternative biofuels originating from biomass with different processes, and I try to summarize the most common ones here. And on top of the list, we have the biodiesel and biojet fuel production, and that starts with the extraction of fatty acids and triglycerides, oils mainly, and then we can go through trans-esterification or direct esterification. We will go into details shortly, and produce biodiesel at the end. Or we can use the same feedstock, same raw material, and go through hydrogenation, then deoxygenation and decarboxylation, quite sophisticated processes. And we can end up with hydro-treated esters and fatty acids, or hydrogenated vegetable oil. They all refer to the same product. And if we want to continue with hydrocracking and isomerization, we end up with biojet fuel. I will give more detail on these shortly. The other one we heard about, pyrolysis. Almeida made a very nice explanation about it, very detailed one. We can obtain bio-oils, can be used for many purposes. And the other one, the popular one, is bioethanol. We all know that it is produced through fermentation, just like we produce beer or wine, all the alcoholic beverages. But of course, it has more sophisticated purification technology. And at the end of the production process, we remove the remaining water, which is azeotropic water, about 4 or 5%. So we end up with a perfectly dry ethanol, bioethanol. We can also produce methane gas, biogas, mixture of gases, which can be used as an energy source through fermentation. More, let's say, sophisticated and popular process through gasification, we can end up with BTL, biomass to liquid, and biohydrogen. These are all different alternatives of biofuels, which can be generated from biomass through different technologies. But now I'm going to focus more on the fatty acids, triglycerides, biodiesel, and SAF, sustainable aviation fuels, and so on. Oops, okay. Yeah. So very briefly, biodiesel is the common terminology, but the, let's say, more technical terminology is fatty acid methyl esters mixture. It is not a single molecule. It is the mixture of fatty acid methyl esters. And here you can see a very nice, I think you can see my cursor. I'm moving it here. I hope you can. Okay, great. It's a mixture of alkyl group. The number of carbons is starting from 12 to 22. And, this is a long molecule. We have a straight chain carbon molecule. And at the end, we have the ester, methyl ester, especially here, one carbon methyl group. And this is a mixture of methyl esters. And we call this biodiesel if it meets certain quality criteria. So how we can produce biodiesel? There are two methods. We can either produce biodiesel through direct esterification, or we can go through trans-esterification. The difference is the starting material. If we have fatty acid mixture as our starting material, then we better do direct esterification. But if we start with triglyceride, which is the most common methodology, by the way, in this industry, we do the trans-esterification. In both of the mechanisms, we use methyl alcohol as the source of the alkyl group to produce methyl ester. And at the end, you can see we end up with a methyl ester molecule, our famous methyl ester molecule. In the trans-esterification, since we start with the triglyceride molecule, we have 3 R groups. That means we end up with 3 moles of fatty acid molecules, methyl ester molecules. And we have a byproduct called glycerol in the crude form. So this glycerol molecule is coming from the backbone of the triglyceride. This is the difference between the two processes. And another difference is if we go through direct esterification, which is not so nice in industry, you need quite high temperatures, high pressure, and a very strong acid catalyst. The moment we mention a strong acid catalyst, try to imagine all the equipment has to be resistant to corrosion. It has to be stainless steel, which makes everything quite expensive as an installation. For the trans-esterification, we're lucky. We don't need high temperatures. It's actually, it produces its own energy after the reaction starts. So there is an exothermic reaction. It releases some heat, so it carries on with its own energy. It is done in the atmospheric pressure, and we need a base catalyst, which is sodium methylate. In this case, that is the most common used catalyst. So this is a simple slide I wanted to show you. After the reaction is complete in the reaction chamber, the moment we take it to a separation funnel or phase separation, we can clearly see the reaction has ended, and we end up with 2 different phases. And the bottom phase is the aqueous phase, which is heavier and carries the glycerol molecules. And the top part is the organic phase, which is rich in methyl esters. Of course, this is right after the reaction, and then I will go into the details. But very roughly speaking, we have 80% glycerol in the aqueous phase, and we have remaining catalyst, and we have excess methanol in both of these phases. So just to remind you, the factories, we call them biorefineries. When we say biorefinery, these are the factories that utilizes agriculture products, crops, food, non-food crops. I put 2 examples here. One photograph on the left is the one we grow in Turkey. That's a non-food crop, rich in oilseed. It used to be a weed in Turkey, and it ended up doing quite well in non-irrigated soil, and it is becoming more and more popular, especially in the weak soil and places where farmers are not so much interested to grow food. The other one is the rapeseed. It is the plant with nice yellow flowers on the fields during springtime in April. And of course, we have the used cooking oils. This is becoming more and more popular for us. And the percentage of used cooking oil is increasing in our feedstock base. And on the right side, this is a picture of soapstock. This is the soapstock, we call it soapstock in industry. It is after the neutralization of the fatty acids in the triglycerides, it is basically a soap molecule. It is the sodium salt of fatty acids. they are being removed, and we can convert them back to fatty acids, treating them with strong acids, and then we can utilize them to produce biodiesel. So when we say biorefinery, we utilize all these raw materials, and basically some biorefineries start even from crushing the oil seeds, oil meals, and they produce crude vegetable oil, and then they process to make it ready for the biofuel production. Of course, used cooking oils collection and pre-treatment is becoming more and more important. And when you crush the oil seeds, we have a remaining feedstock for the livestock, for the animals. So this process, this industry is actually using some resources, but at the same time providing many resources for other industries at the same time. And finally, for my case, in our case, we were producing biodiesel until now, and we are refining the glycerol at the end. And we end up with two clear products which meets all the standards, quality standards. Briefly speaking about a biorefinery, this is a compact size biodiesel plant. This size of plants, roughly 20,000 tons per year. They were quite popular in the 90s. Then these sizes started not to be economic. And before going to the next slide, I'll just tell you, this is a methyl ester production facility with all the units installed. This part is the control room. Usually per shift, there are only 2 workers controlling the process. It runs 24 hours continuously, and a very small lab and administration building is enough, and you have some tanks to run the plant. But as time goes by, as the market grows and the industry grows, capacities started to grow, and now even this 100,000 ton capacity is considered below average capacity in industry. So we see 200, 300,000 tons annual capacities. These are continuous plants. The plant in the photograph is the one on the left side is the glycerol refinery. It is refining the glycerol and producing pharmaceutical grade glycerol. And the one on the right is producing methyl ester, biodiesel continuously. And there is another oil refinery in the back. So just to give you an idea how a biorefinery looks like briefly. These plants are controlled electronically. They are modern plants. They controlled by PLC instrumentation, and they carry all the safety precautions. The plants are X-proof, so there is no spark allowed in the plant. All the equipment, all the electrification is done accordingly, and all the safety precautions are taken, just like in the petroleum refineries. Roughly, for you to visualize what a batch reactor is, this is a 20-ton batch reactor. This is a reactor which works basically in the batch form. It produces methyl ester mixture for 3 hours, and then when the reaction is complete, we can monitor the reaction, and then we immediately transfer the contents to a phase separation tank, settling tank. And then the moment the reactor is empty, we can fill it again and start the reaction again. So this type of process is called semi-continuous process. What we mean by semi-continuous process, the reaction part is batch, but as soon as the reaction is over, we can use 2 separate settling tanks, and then the remaining of the plant can be continuous, the purification part. That's why we call it semi-continuous. These semi-continuous plants are no longer in the industry. I mean, there are few working probably, but I don't think they are competitive enough anymore in the market. So I can tell you most of the plants, almost all of the plants are now continuous production. How is our time, by the way? Okay. Anyhow, you would let me know if I'm too slow.
I think we're in 20 minutes, but
okay. Okay. I'll try to keep up with the pace. Well, very briefly, I want to outline the biodiesel production process. As a starting raw material, I have chosen 3 glycerides. We have the methyl alcohol and the catalyst. These 3 different substances, they meet in the reactor. And after they reach a first initial temperature, which is around 60 degrees Celsius, and there's continuous mixing in the reactor, and then the reaction starts. The reaction starts with the help of the catalyst, and generally in a batch reactor, it takes about 3 hours. When we reach the end of the reaction, because we want to shift the reaction to the product side, we have a lot of methanol in the mixture, and it goes through the phase separation. As soon as we have the phases separated, in both phases, we have excess methanol. Methanol is explosive and it has to be removed as soon as possible. So both of these mixtures, they go through desolventization. Desolventization is a basic vacuum heating vessel, and under the vacuum, methanol is being separated from the mixture. In the organic phase, we have a small neutralization of the organic phase because we have excess catalyst, which is a strong base. So we add some weak acid to neutralize. And then the organic phase goes through the purification processes. Depending on the technology, we can either distill the methyl ester to purify and end up with like 99.5% pure fatty acid methyl ester mixture, or we can go the conventional way. We can do the washing with water and purification, and then it has to go through drying column. Finally, we end up with the standard quality biodiesel. On the aqueous phase, we have our valuable crude glycerol molecules sitting in the aqueous phase. And then if the plant is equipped with a glycerol refinery, that crude glycerol is sent to glycerol refining, and then we can end up with either technical grade quality or 99.56 purity pharmaceutical grade. Very roughly, just to give you an idea about the quantities, if we start with, let's say, 10 tons of triglyceride in the beginning, and more or less 1 ton of methyl alcohol is consumed during the reaction, we end up with almost 10 tons of methyl ester biodiesel, and the other 1 ton is in our glycerol phase. So this is roughly the mass balance. It is about 10% of the inlet, the glycerol. Okay. About the quality criteria of biodiesel, this is the list of quality standards. There are, if I'm not mistaken, more than 24, 25 different quality parameters of biodiesel. Some of these parameters are depending on the feedstock type we choose, and some of the parameters are affected by the technology we use. And just to give you an idea, I wanted to highlight the ones in green can be adjusted with the use of technology. If you have the right technology, you can adjust your fatty acid methyl ester content, which needs to be 96.5% pure. You can adjust your flash points. That means you need to remove the methanol from methyl ester mixture, because flash point is, when you have a remaining methanol in the mixture, then you have a low flash point. The acid value, methanol content, monoglyceride, diglyceride, triglyceride content, these are all related to conversion quality, which means roughly the quality of the technology. And the ones in blue are coming from the feedstock type. So basically, there's nothing you can do. Whatever technology you use, You cannot change these figures with the technology. So a very careful recipe preparation is necessary for a successful industrial application, because each feedstock type has certain criteria. And at the end of the day, if you're running a factory, it has to be economic and it has to meet the quality criteria continuously. So you need to make a very good blend of the feedstock which is available to you at that time. It can be used cooking oil, it can be a crop, non-food crop, food crop, or it can be a fatty acid mixture. So a very careful examination of the feedstock quality needs to be carried out before going into the production. So I need to speed up a bit. This is the hydrotreated esters and fatty acids, hydrotreated vegetable oils. That means the green diesel, renewable diesel. These are alkane molecules. These are straight chain alkanes, around 8 to 21 carbon. We can say this is a perfect diesel fuel. It doesn't have any aromatic, it doesn't have any naphtha in it. It is pure alkane, and it has some superior qualities to commercial diesel fuel. A few words about the production of HVO or hydrotreated esters fatty acids, and then biojet fuel, sustainable aviation fuel, if you wish, SAF. We again start with the triglyceride molecule. Our happy famous triglyceride is here. It is an unsaturated molecule, just for your reference. We have hydrogen gas here, and it goes through the saturation, hydrogenation. So we saturate all the double bonds here. And at the same time, we split the molecule, and we have 3 moles of fatty acids, if you can see. And there is a propane molecule leaving the group, because the backbone in this case is not a glycerol anymore, but it is an alkene, which is a propane gas, valuable molecule leaving the reaction. And then we have option to go either through deoxygenation, which needs plenty of hydrogen gas. And with this hydrogen, we can remove the water and end up with 3 moles of 18 carbon alkane. Or we can go through decarboxylation, and we don't use any hydrogen, but we end up with losing 1 carbon molecule for each alkane molecule. So we end up with 17 carbon. Of course, there is some energy difference between these 2 molecules. This is purely commercial decision, and depending on the feedstock, on the preferences. So basically, at the end of these 2 processes, we end up with a straight chain paraffin mixture. It's a perfect diesel fuel. Then we can go through hydrocracking and isomerization to obtain smaller and highly branched molecules. Highly branched molecules are so valuable in the field because they have very high improved cold flow properties. You know, for the aviation industry, up in the air, we have minus 45 Celsius degree. So the fuel has to be in the liquid form. So the moment we have highly branched molecules, it can resist to minus 45, minus 46 degrees. It can even be better than Jet A1 fossil fuel aviation fuel. So after the hydrocracking and isomerization process, we end up with splitting 4 different, let's say, segments. We have the light fraction, gasoline fraction, the aviation fuel. Depending on the process, it can go up to 70%. And we can, again, produce diesel fuel, green diesel fuel with this process. All these decisions are based on the market conditions, on the economic considerations, but this is roughly how it is produced. Well, now briefly about the future of biofuels. This is from the International Energy Agency. In 2019, we have reached more than 160 billion liters of biofuel production globally. With the help of COVID, unfortunately, it's minus 15% almost down. by the end of 2020. But hopefully leaving COVID behind, we are expecting a recovery in 2021 and then a gradual increase in the years to come. As you can see, the increase will come basically from all types, but mostly from the ethanol, bioethanol, and hydro-treated vegetable oils, the green diesel. The reason why biodiesel is shifting to HVO is there is a blending wall, let's say, up to about 10% blending by volume. Biodiesel being blended to diesel fuel starts to have some, how to say, technical difficulties. So, the moment we switch to HVO, there is no ceiling, there is no limit. We can use it as a drop-in fuel. It can be up to 100%, just like the aviation fuel. There is no limit. Well, looking at the ethanol production in the Asian markets, this is for me quite interesting. We are expecting to see a big increase in China, more than 8 billion liters in 2023, 4, 5. In India, there is an increase expectation, and in Thailand as well. In the biodiesel and HVO production part, there is again an increase, but no surprise with the help of the feedstock availability. Of course, in the United States, you know, the most common feedstock is soybean oil. In Indonesia, palm oil. And in Brazil and Argentina, we have soybean oil as well. And in European Union, again, we are expecting some recovery, but not as much as in US or in Indonesia. But looking at the numbers, the first graph was roughly telling us what to expect in the future. Briefly looking at the fossil fuel side in the EU, I want to concentrate a bit in the European Union now. Starting from 2006, 2007, until the end of 2030, we are expecting to see about 20% decrease in the fossil fuel consumption. This is quite dramatic, and this decrease is mostly coming from the gasoline. No surprise, the transportation is switching to electricity. But this much of switch to electricity is a bit surprise to me, but these are the expectations. And we see a bit of increase in the aviation fuel kerosene usage because of the aviation industry. And diesel is more or less the same. It is slightly decreasing, but towards the end of 2000, let's say 28, 29. There is a directive in European Union to subsidize and to support the biofuels, in specifically biodiesel and HVO. Currently, there is 10% requirement of biodiesel blending. Out of this 10%, 7% is coming from the crop-based fuel. The remaining is coming from sustainable resources using ISCC certification. This is the most common one we use here. What we use here is ISCC certification, which is certifying the sustainability of the feedstock. And the color difference is the orange part is the real usage of the biofuel, and the light color is the double counting volume. So European Union is basically saying, if you are using 1 unit of sustainable biofuel, I'm going to count it as 2, so it is going to fulfill your requirement. Basically, this is an additional subsidy given to the certified, sustainably certified biofuels. And in years to come, you can see the advanced biofuel is increasing. The remaining is almost the same, not much change. And all the increase in the percentage is being expected from the advanced biofuels. Advanced biofuels, I hope you're not going to ask me what are the advanced biofuels, but I think these are the, biohydrogen, fish and productions, bioethanol produced from cellulosic material and so on. Some more detail about the biodiesel production in European Union. The capacity was higher in the beginning. In 2011, it was about 25 million tons. Now the capacity, the installed capacity is about 20 million tons, but the capacity usage is about 50%. In 2019 and 20, it went down a bit further, around 50%. The blending ratio is roughly 7%. This is how it looks in European Union. So more or less, European Union is using about 15 million tons of biodiesel annually. And this is roughly telling us what type of feedstock is used in European Union. Don't worry, I'm going to translate them there in Turkish. The majority is coming from the rapeseed oil, the canola, we call it in Turkish, rapeseed oil. More than 40%, and the quantity is not decreasing, it is in the increase. Palm oil is decreasing. We see less and less palm oil is being used in the consumption, not in the production. This is the consumption figures of the European Union. We have happily seen more and more used cooking oil is being used and utilized. And out of this 2.7 million tons, almost quarter was collected in European Union, and the third quarter was imported to European Union. We have 6% animal fat, tallow, about another 6% soybean oil, which is decreasing as well. The animal oil, animal fat is increasing. And we have another remaining 6%, which does not change much, but it represents basically all other oil types, all the other small type feedstocks. This is an interesting table I wanted to share with you. It has some hope in it. I like these numbers because what I mean, it has some hope in it. When you add up the figures, the collected volumes in European Union, it hardly meets 700,000 tons. But when we look at the prospect, when we look at the future of biofuels, we need much more than that. It is obvious, and we need to switch from definitely from food crops, but also from the agriculture slowly. But when we look at the figures on the right side, this is quite optimistic. The Holland is being the #1 in European Union. They are collecting 3.6 kilogram of used cooking oil per year per person, and Turkey is being on the bottom of the list, unfortunately, here. But we are now collecting 0.4 kilograms. But let me tell you, I mean, this is something nice. I see something nice in it because the population of Turkey is about 75, 80 million. So the moment we increase this quantity to, let's say, 3 kilograms, here on the left, Turkey is on the 7th, but probably it's going to, I don't know, change all the numbers in European Union. And of course, all the other countries as well. I mean, the other countries, slowly, they're increasing the collection volumes. And we can see at least one thing for sure here. There is room to grow. We can easily double or triple or even multiply 4 or 5 times these collection volumes in the European Union. And this is an area where everybody is focused on at the moment. This is in Turkish. I'm not going to spend time on it. We're basically, if anybody wants to ask why you're producing biofuels, what is the benefit of biofuels for the country, for the humanity, these are my answers. But if you ask, I'll come back to it. I don't want to spend much time on this.
Also,
this is
sorry, but since we also have questions, if you could wrap it up, it would be really good. Sorry to interrupt.
No, it's okay. I am almost finished. Very briefly, what I believe as the future of biofuels, I think we're going to see some increase in the efficiency, yields for the agriculture production, correct land use, in order to prevent this biodiversity issues and so on. And we will have better crop rotation to increase the efficiency and the yields. Of course, we are going to see increase in used cooking oil collecting and utilizing other resources. We will have more efficiency in the storage and refining the feedstock. Definitely the feed production is increasing for the livestock, and finally we will have more biofuel to be used in the transportation. And of course, two important things to support these changes. We have to make this sustainable and through certifications. And the industry needs to carry out the economical and environmental impact analysis continuously. And finally, for the chemical engineers, if there are any, I am chemist, I'm not engineer, but running a plant after so many years, very brief recommendation: if anybody wants to run a biofuel plant, it has to be efficient, very efficient. The philosophy of producing biofuel, you should need a very low quantity of energy, and the water consumption is a very, very important item on our agenda. It has to be very safe, of course. Continuous and sustainable production at standard quality is a must for the economic success of a plant. And if anybody is interested to produce biodiesel, I would highly recommend to combine it with an oil refinery and glycerol refining. Otherwise, it is really hard to meet the economic expectations. Yes, this is the end of my presentation. Thank you for listening. I hope it was not too much on the surface. Yeah, thank you.
Okay, so thank you for the presentation, Mr. Borovalı. Now we will move on to questions. So the first question is, do you see biohydrogen or hydrogen generated from renewable energies as the future source of energy, especially in transportation?
Definitely. I already know some of the automotive manufacturers are starting to use hydrogen as a source of energy. For the future, I see biohydrogen as a source of energy, definitely. But this is where I have the difficulty. From the academic community, when we speak about the future, I need to be very realistic, and I need to keep my both feet on the ground. I don't know how close biohydrogen is. I am 50 years old. I'm not sure whether I'm going to see any hydrogen fueled car on the street, but definitely the progress is optimistic. Yeah.
Okay, thank you. Now, the next question is, what is the status of biorefinery projects in the Indian subcontinent especially? India has a great amount of agricultural waste, which is capable of producing biofuel.
Yeah, as far as I know, India is becoming more and more important producer, especially on the used cooking oils and the feedstock, which can be used as non-crop. India has a very advanced chemical technology, and we have some very good Indian engineers in Turkey as well during the startup of these plants. As far as I know, India is also very advanced in vegetable oil refining. Considering the population of India and the consumption, the food consumption, the oil consumption, I think India is going to be one of the most important countries in either HVO or in biodiesel.
Okay, thank you. Now, next question is there concern over competition for raw material between the energy and food industries?
Well, this is a very good question. Yes, but there are ways to avoid these competitions. Normally, with the good philosophy and with good planning, biofuel production it was maybe 15, 20 years ago when it was first into our world. The food and fuel is, there was debate about food versus fuel and so on. Now these debates and these discussions have become meaningless because there is no meaning of making a food versus fuel discussion. Of course it is food. I mean, there is no question about it. And but interestingly, with the help of biofuel industry, the food production has increased enormously. And now what we can see in Turkey and also in other parts of Asia, there are lands which is not used for food crops because they are not competitive enough and so on. So there are so many ways to avoid food versus fuel debate and competition between food and fuel. Currently, as an industrialist in this field, for many years, we don't have any competition, and there are certain crop types which we never use in the biofuel production because they are so expensive and economically it doesn't make sense at the same time. So the economy of these, the mathematics also brings a solution to this problem. Everybody is trying to use the cheapest feedstock, which is the soap stock, used cooking oil, and the remaining, basically.
Okay, thank you. Now, next question is, how do you think biofuels such as biojet fuels will impact the transportation and other industries?
Well, how they're going to impact other industries? Well, I don't know. I mean, about the other industries, but I can see for sure all the aviation companies are, first of all, the plane manufacturers are switching to more economic planes. And as far as I know, International Aviation Agency made a 20% decrease target in the energy consumption during the flights. And this 20% is going to come not only from using biojet fuel, but the majority is going to come from the new design with a more economic design of the planes and so on. This has already started taking place. But the use of biojet fuel is going to take a certain percentage from the fossil fuel consumption. And I don't expect to see more than, on the most optimistic scale, 8% share in the biofuel, in the fossil fuel mixture. So for the biojet industry, I'm not sure. I don't have any answer how it is going to impact other industries. I don't expect any negative impact for sure. Most probably there will be some positive impacts on the raw material side and technology improvements.
Okay, great. Now, the next question is, which companies and countries should invest in the biofuel industry more?
Well, that's a very good question. I think all of the countries should invest in biofuel industries. This is a field where everybody needs to try to prepare solutions. And with the investments and with the progress of the industry, every year we see efficiency is increasing, prices are decreasing, the markets are becoming more and more competitive. I mean, of course, whenever you want to make an investment in an industry, the first thing you look at is the availability of feedstock. So availability of the feedstock is the primary criteria, I would say, as an investment criteria for the countries. But it is hard to differentiate any country. I mean, I wouldn't leave any country out of these investment period. I think every country should prioritize the fuel type and the availability of the technology and the people, the available engineers in the country, because these industries they just don't develop by themselves. The moment you have a biofuel industry, it affects and it triggers many other industries, food industry, animal feed industry, many economic impacts on other industries.
Okay, now next question is is there a specific type of solvent and catalyst used in the transesterification reaction?
Well, yes, we don't use solvent. I mean, methanol itself is dissolving in the alcohol, so in the oil, sorry. There is no special solvent. And for the catalyst, the commercially available catalyst is the mixture of sodium hydroxide and methyl alcohol. But the moment you try to make it by yourself in the factory, you can easily mix sodium hydroxide in the pellet form with the methanol. Then you end up with some water molecules in the catalyst, and that water molecule is interrupting your reaction. So commercially available solvent is a reactant methanol, and the other one is sodium methylate. Sodium methylate is 30% concentrated, the rest is methanol, so it just dissolves in the mixture.
Okay, and the last question is, why do industries use batch reactors for transesterification reactions?
Well, batch reactors are always easier to use, especially during the first stages of becoming familiar with the process. Batch reactors are the safest in terms of controlling the reaction. You can play with the duration of your reaction. You can play with the amounts of reactants. You have more, how to say, control on a batch reactor. And of course, the other good part of it is in case you fail in a batch reactor, there you might find some ways to recover the feedstock, recover the raw material you used in the tank, and you can start again and try to reach the end product. Initially, it was easier, more. It served more, how to say, control functions. But as time goes by, the batch reactors are not serving the high capacities, and all the industry transformed to a continuous production. Once you feel quite confident on the production, and especially if you remember, I emphasized the recipe formation, the feedstock mix. If you feel confident, then you can start feeding your continuous reactor. But one thing to be careful, once you start feeding the continuous reactor, it is a pipeline. It just carries on, and there is a risk of ending up with a low quality product. So usually this is how most of the industries start.